Energy Institute of Engineering and Technology. Today's session we are going to start with the Fermi golden rule and exciton. So basically, before we start with the topic, Fermi's golden rule. Now Fermi's golden rule basically it's correlated with what? It is correlated with the quantum physics that is being utilized to calculate the transition rate. Okay. Now the word transition rate comes, so it should be in your mind that transition is between that absorption and emission that we were discussing. So electron is gaining energy, going to the high energy level, and then coming back by emitting the energy. That are the transition between the two energy levels. Or you can also say that this theory will be concluding you the probability of the transition per unit time. So again, it will be calculating the possible ways or the possible outcomes for the transition. So in general, Fermi golden rule can be applied to, it can be applied to the atomic transitions, okay, and also the nuclear decay and the scattering. So these two things can be applied with the help of the Fermi golden rule. So the next part, the transition rate depends on which thing? The first part, that is coupling between the initial and the final state. Now whenever I say initial and final state, always take that initial state is the lower and final is the higher energy level state. For our context, we can also say that it is E1 and E2. Okay. Now the number of the ways the transition can happen. So these are the transition rates where the things can actually work out. So now the transition probability is given by basically is nothing but the your wavelength, that is lambda IF is equal to 2 pi by h into mode MIF square ZF, where you can say that lambda IF is nothing but the transition probability, MIF is nothing but the matrix element for interaction, ZF is the joint density of states, and H is the Planck constant. Now why the joint density is there? Obviously we always have till that the transitions are always multiplied by the density of the states. Okay. So now this above equation, that is nothing but the Fermi's golden rule, that will give you the transition probability between the two states. So the coupling term is called as a matrix element for the transition. Now what does that mean? It is an integral term where the interaction is expressed in the form of potential, that is V, that is nothing but our potential difference, which operates in the initial state of a wave function. So now the transition probability is proportional to the square of the integral of the interaction over a space appropriate to the problem. So again, we are taking the integral part, that will give you MIF integral part of psi star f V psi I d of V. Okay, where we are taking that V is nothing but the operator of the physical interaction that covers initial and the final state. Okay. As well as psi star f is nothing but the wave function of the final state, and psi I is the wave function of the initial state. So when we are taking this as in consideration, a transition can be proceed more rapidly if the coupling between the initial and the final stage is strong. So if this transition or the coupling between these two stages is strong, so the transition would be very simpler for that, and it would be comparatively very rapid in nature. So the transition probability lambda is also called as a decay probability and is related to the mean lifetime, that is nothing but your tau. So now lambda, that is nothing but the transition probability, is equal to 1 by tau. Okay, so this is the mean lifetime, and this all terms have also come in the laser also. Okay, in the laser basic term. What is the mean lifetime? What is the decay probability? So this all terms are correlated to each other. Now the next term we are going to discuss, that is nothing but an exciton. What is basically an exciton? The concept of exciton was first proposed by Yakov Frenkel in 1931, which gave the proposal that it is the bound state between an electron and the hole which are attracted to each other by electrostatic Coulombian force. Now the thing is that we have always in mind that there is an electron and electron pairs are there, that is Cooper pair we have discussed. Then you also get the attraction level of the holes and the electron. But here something new was there, and that was that there was one attractive force between this electron and hole that was there, and it may be differing with the respect to the distance also. Okay, so how they were attracted? Because of the nothing but other than electrostatic force. Okay, so how it was doing it? So let us understand how it is an excitant form. So when an external energy, say a photon, is absorbed by a semiconductor electrons, it moves to the conduction band. That is a simple creating electron hole pair. Okay. So now this electron is now attracted to the localized hole by a repulsive force from the large number of electrons surrounding the excited electrons. Okay. So it means to say that when the electron has actually gone up, okay, so still there is some force acting between them. Okay, and that is nothing but some localized repulsive forces. That is how the exciton is actually formed. Now this attraction provides a stabilizing energy balance. So how it is providing, you can see that this is the exciton, that you can see that it is, as mentioned in the previous one, that it is going from the lower energy level to the high energy level. Okay, and there is some bond between them, that is nothing but the electrostatic bond. Here you can see that the ring time thing is there. Okay, and this is the attraction that provides the energy balance. Now let's explore the types of the exciton. Say that the first is nothing but the Frenkel exciton. That Frenkel exciton is nothing but, you can see that all electron is there, okay, and it is just surrounding that particular atom, and that is a hole. Okay, so what happens that when there is a strong electron hole attraction and the electron hole are tightly bound to each other, okay, so you can say that that hole and electron are tightly bound, means the distance is very less. So that type of the exciton are nothing but your Frenkel exciton. So again, it is nothing but the two bonds. Okay, we know that what is the bond after all? After all, bond is between the electron and hole pair. Okay, so this bond between them, the distance is very less and they are tightly bound with each other. At that condition is Frenkel exciton. Now, what are the properties of the Frenkel exciton? You can say that they are tight bound excitons, means distance will be very less. Secondly, they are found in insulator and the molecular crystals. They are binding energy in a range of 0.1 electrovolt to 1 electrovolt available. Lastly, the bound or the specific atom were move on hopping one atom to the another. Okay, so these bounds are actually hopping in nature, when which moves from one atom to the another. And the last property is that they are stable at the room temperature. So let's take out with the next one, that is nothing but the WANNIER-MOTT exciton. So you can see from the diagram itself only now, the distance is very high. Okay, so when an electron hole separation is much larger than the lattice constant, those all exciton are nothing but the WANNIER-MOTT exciton. Okay, so you can see from the diagram that the distance is very high, and in the case of the Frenkel, what was the scenario? That they were tightly bonded with each other. So now again it would be having the properties. So first property, they are called as the free exciton. Second property goes that they are found in the semiconductor. See, previous was found in an insulator. This is found in the semiconductors. Their binding energy is around 0.01 electrovolt, which is exclusively less than compared to what we are having in the Frenkel exciton. They are also delocalized states that can move freely throughout the crystal. And lastly, they are stable and cryogenic in temperature. So these are the properties of the WANNIER-MOTT exciton. Now basically, in this theory that we have discussed is nothing but about the probability of what? Probability of the transition we have calculated first, and second, it was all about the exciton. So hope you guys have understood this session very well. See you in the next session.